Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning, everybody. It's a great pleasure to have Pascal Foua with us today. And Pascal has visited us several times at MSR in the past. I've seen several of his talks over summer. I mean, he's a professor at EPFL, where in the Computer Science School of Computer Science and Communication, and he has been there for almost 20 years now, I think, since 1996. Pascal heads the computer vision group there, and with his colleagues, he works on several topics: feature learning, feature matching, object detection, tracking in video, human body modeling. And Pascal has co-founded two companies. Pix4D, which many of you may have heard of, does dense aerial 3D mapping from UAVs. And has the other company that he has founded, Playful Vision. They build tools for video analytics for several sports scenarios. And so Pascal also happens to be an avid glider pilot. And so today he's going to talk about learning local features. So welcome, Pascal.
Thank you.
Yeah.
So I've been at EPFL for almost 20 years now, and for about 15 of these 20 years, we've been worried about interest points. And of course, I mean, I probably don't need to explain why they're important. They've played a very, very crucial role in many applications in computer vision. And by and large, it started at the end of last century with David Lowe. And since then, there's lots and lots and lots of citation, lots and lots of papers. We've all been essentially running after David with actually fairly limited success. I mean, SIFT, 17 years on, is still pretty good. And most of these approaches, we all use essentially the same pipeline. And the pipeline is, you start with an image, you run a feature point detector. For every feature point, you compute an orientation. You use that to warp the patch. You compute a descriptor, and you can compare those descriptors. So over these 17 years, I mean, there's a gazillion papers, and this is really important, ... And they are also, so these are papers about the whole pipeline. And there are also a great many papers, including ours, about various elements of the pipeline. So the local feature detector, actually about the orientation, not so many. I'll come back to that. And lots of papers also about the descriptor. And we've all been guilty of the same sin. So we develop one of these algorithms. We test it on some database, and we are very happy because our ROC curve is above that of the others, so we get a CVPR, an ICCV, or some such paper, which helps with tenure, but doesn't help that much with science, because in my experience, what happens is once you take your little block and you put it in the whole pipeline, the overall improvement is not that big, which essentially is why SIFT is still around. So that's kind of the background. And of course, in these 20 years, something else happened. The invasion of deep learning. So I must confess, to this very dwindling group that's still a bit skeptical about the whole thing. That's kind of the way I perceive them. However, I mean, you have to live with your times, and if you can't beat them, well, join them. So that's what we've been doing. And actually, what they do is they offer a way to reformulate this whole pipeline into one formalism, the CNN, the deep learning formalism. And then, in of itself, I don't think that matters all that much. But the reason it matters, or it's going to matter, is then you can engineer the various elements so that they work well together. And that's where the benefit is going to come from. And so that we can put at the end one more set of graphs, say, our performance is better than the others. So we are still guilty of the same sin. Okay, so let's look at these three elements: the feature detector, the orientation estimation, the matching. I'm going to reformulate each as a CNN, and then we'll put them together. Okay, so first, the key points. How would you detect them? And this actually all started a few years ago from a problem like this one. You take two pictures of the same scene, in this case it's Frankfurt in Germany, and you try to match them, and they've been taken at different times of day. Actually, one is by night, the other is by day, so really strong illumination change, and their SIFT doesn't work. You cannot really, or surf, I mean, it's the same kind of thing. And why doesn't it work? Well, what the failure point is here, is if you look at a little window here, what you will find is you don't find the same interest points in both images because the illumination is so different. And so at that point, if you have even the best descriptor in the world, it's not going to help. You really need to find the same key points in both images. So that's the problem we've addressed by trying to find something that would truly be invariant to light changes and, of course, to geometry as well. I mean, you want invariance to both. And so that in this case, for example, the key points we find, so of course we don't find exactly the same, but we find enough of the same so that we can do our work. So how do we do this? Well, what we are going to do is to use webcams that are fixed and take the same scene over and over again, but over a period of time so that conditions change. And so that gives us a bunch of images. We are going to superpose them. And of course, even with a webcam, it vibrates a bit, so it's not exactly the same viewpoint, but that's easy to correct for. So we can assume that one point in the image is really the same physical point in the whole stack. And then we're going to do something extremely simple, is to say we want to find the points that are highly repeatable. So in this case, we're going to use SIFT, in fact. Find SIFT key points, or anything else, it doesn't really matter. And in each column where the point appears often enough, we're going to, this is a good key point, I'm now going to train a detector that finds this key point in all the images, not in most of them, in all of them. And then separate those key points from everything else. And it turns out this is not particularly hard to do. You just have to, you define a loss function. So that says, I want essentially the same response in a column. It's either always 1, always 0. And given what descriptor you want, you also want the response of the descriptor to be the same. So you can train it to work well with, say, SIFT. And it turns out this is fairly easy to implement with a shallow net that gives us this point detector that we call tilde. So that's training. At test time, we just run it on the image, do non-maximum suppression, and get our results. And then we can actually use it to register images that have been acquired at different times of day. So here are some examples. This is various scenes. And we try to find, for example, where this is, this actually is there, but we can use different versions of this one and show that we can register in a very stable fashion no matter what the weather was that day. So here an example of a little video where we do this over the space of a year. Yes, it vibrates a little bit, but by and large, it stays where it should be. So for example, if we think about, since we're going to talk about drones later, that's important. The drone has to fly every day in any kind of weather. Okay, and of course we can do this in a more, we run on the usual databases. We can show that we outperform in terms of the usual repeatability measure. We outperform the others. And one small detail, there are 3 versions of tilde here, because what I've shown is just a regression problem. So you don't have to use a CNN to do regression, actually. When we started in the dark days of before CNNs, this was a tree, a gradient boosted tree. And yes, as usual, we have the same experience. It works, of course, but we do get better performance when we do it with a CNN.
Till the CNN and till the P.
Yeah, they are subtle. P is also a CNN. It's a better CNN. But,
Would you comment on the computational efficiency compared to set or other detectors?
It's not, so yes, I'm going to do that. For the detector, I don't remember the numbers, but for the descriptor I'll talk about later, it's about 4 times slower. So it is slower, but it's not massively slower. And since, and it's on standard hardware now, there's all this hardware that's optimized for CNNs that's coming out, so I don't think it's going to be an issue.
But the detectors tend to be, well, at least around the times that SIFT was around, detectors tend to be very similar, right? You used to do Harris Condors.
Right.
And they were like few matrix multiplications, right?
Yeah, they were very fast. So we've used a lot the one that's called fast.
Right.
Precisely,
fast,
because, and it, yes.
I just wonder how many layers of your convolution network.
This is really, this only has 1 layer. It's a really simple one. Yes?
One question about this. So, if I understand correctly, all these data sets are mostly from the same perspective.
Exactly, this is the same.
Right. Have you also tried getting other data sets with more perspective changes and ground truth? So that
okay, so for this, no, we haven't. But for what I will show next, yeah, so we could go back. But I'll show you in a moment that we use phototourism data sets, and perhaps we should have done that there, but we didn't. Okay, so in short, we really want our key points to be repeatable, and we can train a regressor to do this for us. Okay, so that was number 1. Number 2, let's talk about orientation of patches. And if you look at this list that I showed earlier, there's something fairly striking. So lots and lots of paper, ... lots and lots of papers. Almost nothing. We may have missed one, of course, but we really tried, we only found 1. And if you look at all these other papers, they do mention, SIFT, of course, mentions orientation in terms of the dominant orientation of the histogram, but it's 1 throwaway line somewhere in the paper. So it's important, and it has been largely overlooked. And what I'd like to show now is by actually looking at it a bit more closely, you can actually get a boost. So first, before I tell you how we do it, what does it mean? What is orientation? It's actually, if you think about it, the orientation of a patch is not very well defined. Because here's an example. You have a patch, and you have, what is the orientation of that patch? There are at least 2 dominant orientations in this one. So you have to pick one, but which one? Okay, so In fact, our definition is going to be just as arbitrary, but it will serve our purpose, which is we are going to try to find the orientation that gives us the best matching performance, because that's what we want to do in the end. And so what does this mean? It means that we are going to have a Siamese network so that given a patch or given a patch of the same thing is always going to return the same orientation. And that orientation is the one that will allow, given a particular descriptors, again, let's say we are using SIFT or anything else, but SIFT for the time being, we want this, our network return this thing called orientation. We want it so that the distance between the descriptors is minimized, because that's what we'll use to do the matching. And we train the regressor to do this. And one catch about this is to train it, we need to do backpropagation, means we need derivatives. So we need to be able to differentiate this expression. And if you think of SIFT, well, SIFT is not exactly differentiable. So what to do? Well, what to do is to pre-compute numerical derivatives before you start, make a big table and use them in the computation. So it can be done, we've done it, but it's actually a bit cumbersome. And we'll see a bit later that if you replace SIFT by a CNN that is differentiable, it makes the implementation a lot easier.
So here you're fixing everything but the parameters for the orientation?
Exactly. So the descriptor is given at that stage.
But you have to enforce consistency. I guess I missed that, right? Like you want the orientation to be discovered to be the same every.
Yeah, so we have several versions of the patch, and it will predict an orientation per patch.
For all the versions, it will keep
Right.
the same.
Yes. And it helps. So, for example, in this case, we are using SIFT to do the matching, but we compute the orientation either using the standard dominant gradient of the normal heuristic or ours, and we do get a lot more correct matches in that case. So this is not quite as significant, but we've tested it to, as usual, on the usual databases. And what we see is that if you get to, we use one of the standard matching performance measure, the old Mikolajczyk and Schmidt thing. If you use SIFT, you get this kind of performance. If you use our orientation instead and the same SIFT, we get a boost. And there are two versions actually of our thing. So one uses the usual ReLU activation function. And this one, GHH, uses an improved version of that where the thing is piecewise linear, where you actually optimize for where you put the brakes. And that gives you a further, not that large, but visible boost.
Any intuition, why is that the case?
I think because it's simply a richer description than before. And the same thing for using VGG. VGG is the Simonian and Zisserman one, which is the one I think that does a bit better than SIFT now. And we get, again, the same kind of boost, which is we use the published version, or the published version plus our orientation estimate.
Were these trained independently?
Yes. Okay, so in short, orientation is important. It's been overlooked. And if you pay a little bit of attention to it and try to compute it with a view to boosting performance, you do. Okay, so last step, the descriptor. Yes.
So even in the beginning, when you're talking of the unified pipeline, the there's a certain way these feature learning methods are trained. There's a task that you have to on your validation set. You're given patches, and you have to basically predict the correct match. So the validation and everything seems to be at a patch level.
Yes.
So in all the previous works, if I understand correctly, the feature learning is always kind of looked at as in this world of patches, but not on the high level problem of matching. Can you do you see what I'm
I think I see what you're saying, and I think we do this. We still at the patch level.
Still at the patch level, right?
But everything I'm talking about right now is patch level. And I'll get back to your question when we talk about training the whole pipeline. Okay, so the final thing, which is how do you compute a descriptor that essentially minimize the distance between corresponding matches and maximize the distance between non-corresponding ones. And so I even have the word patches here, so really it is patches. It's just, again, that you can do with a Siamese network and the appropriate loss function.
Do you balance the data out?
Yeah, I was going to ask.
I'm sorry?
Negative data.
Yes.
Basically, for every match, there are n-1.
Yes, there is balancing, and there's also hard mining, and all these issues are, yes.
There need to be. I guess details and
They are addressed. So actually, that's why this one I have the actual network on the slide, and I'm glossing over the details, but I know that when they did this, it spent a good long time trying every single. I mean, that's actually, I find it's very frustrating about this kind of work. This is the final result. It works. And they used, I don't know, they used 10H instead of real U because it works better. And why is that? Well, I don't know, but that's the way it is. And it took them, many months to come up with that particular thing that does the job. And one thing, so there are no fully connected layers in this thing. And yes, essentially what you said, normalization, hard mining is key. If you don't do it, it doesn't work. But when it's done, you don't need to retrain it again. This is essentially a replacement for SIFT. Of course, which captures the biases of the particular database you've trained it on. And so just to do a bit of, again, testing, we used the Brown dataset, the Liberty dataset by Matthew Brown and company. So it has actually 3 sets of patches, 2 from Liberty and Notre Dame, are essentially architectural things. And the third one is from Yosemite. So these 2 are similar, this one is different. And we train on 2, test on the third. And these are the kind of results we get, which is on this data set, actually, we don't do that much better than VGG. It's sort of comparable. And actually, you can understand why. It's the usual, the one we do worst on, we do worst. We're here. We're not completely at the bottom, but we're not winning. Is if you train on Liberty and Notre Dame, you train on 2 data sets that are similar, and you test on the third one that's different. It doesn't work. It doesn't work as well. It works better if you train on Yosemite and Liberty and test on Notre Dame, say. And it does work better also. I think this data set do have a number of, I'm not sure they're all that representative. So when you go to different scenes, then we do better, we generalize better.
So the architecture is the same, only the data set.
Only the training data sets are changed.
And does it make sense in the sense that, when you have a neural network, you should be training on everything you see?
Absolutely.
And then,
it's a matter of, yes, we should. In the end, and I was visiting David Lowe yesterday at Google, and said, in the end, we should train this on their full Google Earth thing, and the problem is, I don't have the full database, and I don't have the computer resource to do this. But yes, you should.
So, clarification question. What does VGG mean? You're using the VGG output as the feature descriptor?
No, in these are the published.
The Simonian and the Gaudi.
Right.
But this was not deep learning, because now the VGG refers to this deep net thing.
Oh, okay. I got confused because there's
So
VGG.
This is so Simonian and Vivaldi. It's
the feature descriptor. Okay.
Yeah, the feature descriptor.
I see.
Yeah, I think of all those we've tried as baselines, that's the one that works best.
I was confusing it with the other, which is a network for object detection. Yeah.
Okay, so we can, again, we have now the third piece, which does well on its own. It generalizes, and so that was the question, the earlier question in terms of computation time on ordinary hardware. It's actually a bit over 4, it's more like 5, but what's a factor 5 between friends? I mean, once NVIDIA gets to it, it'll go away. Okay, and this is a potential replacement for SIFT. Okay, so now we have our 3 pieces. They're all CNNs. So check, we are deep. And now we can put them together. And this is the pipeline the end pipeline. So essentially we have the 3 elements and we need to glue them together. And the 3 elements are differentiable by definition, they are CNNs. But since we want to train the whole thing, we need end-to-end differentiability, which means the connectors have to be differentiable also. And that actually can be done. So the 2 main ones are when you do keypoint detection, you do non-maximum suppression, so essentially an argmax. And we replace argmax by something that's called soft argmax, which is equivalent to putting a Gaussian on the thing, and it makes it differentiable. And the cropping and rotation operations, we use spatial transformers, which also are CNNs, and so we get our desired end-to-end differentiability. And now, of course, we have to train the whole thing. So we need key points and non-key points. We need pairs of corresponding matches to guarantee that we get the same orientations. And we need pair of corresponding and non-corresponding patches. So what this means, we actually going to have a bunch of loss functions to guarantee all these things, which is going to make for a really complicated landscape. And what we train it on are these phototourism data sets. So that gets back to your initial question. We didn't do it for TILD. We could have, we should have, but we do it now for the whole complete thing. And the 2 we've used, just for convenience purposes, the one that were available. One is images from Piccadilly Circus in London, images from the Roman Forum. We run an SFM, a structure for motion pipeline. And we essentially, key points, our positive essentially, are going to be points that SIFT found in several images, for which we can reconstruct 3D points, and we can reproject these 3D points in the other images so that we can actually make it find points that SIFT didn't find. But this is a bit limited, so we will find points that SIFT found in some images but not others. Points that SIFT never found, we will not find either. So that's probably a limitation that, I mean, we could think of a way of doing this better, but it's not done.
Have you considered synthetic data sets in order to get around some of these data?
Okay, not in this work, but something we can discuss if I talk about drones. So we have, to train a drone detector, And there the problem is, it's very hard to do all these illumination effects so in a really realistic way. So we found that you need, actually, yes, augmenting with synthetic helps, but you have to be clever about the way you mix the synthetic and the real. And I mean, maybe afterwards I have some other slides about that I could show. Yes. Okay, so here's the training architecture. So we have the pipeline, and we are going to be not a simple Siamese. Now it's a quadruplet Siamese. It's a bit painful because we need to capture all of this. Basically, we're going to train for matching patches around interest points, patches around an interest point that is not matching, and something that's not an interest point at all. And we want different behaviors for all these things, which is why we need these 4 branches. So they are Siamese, meaning this W here means that the weights are shared. And we have, basically we optimize something that's a sum of loss functions that encode all these things. And the end result is we have something that's really ugly and that we just can't train from scratch. Well, at least we tried and it doesn't work, or we were not able to make it work. And so we are not going to train it from scratch. We are going to design a specific training procedure, which essentially goes in reverse. We're going to train for the top. So first, we train the descriptor using the original SIFT matches. So the final thing of the network using, I've shown you the Siamese network. You train the descriptor. Now that the descriptor is trained, you can train the orientation estimator because the orientation estimator is trained given the descriptor. And that's actually a bit easier than what we did before because, as I said, now the descriptor is differentiable. We don't need to pre-compute stuff. So the training procedure is a bit simpler than before.
So you stop the feedback, the backprop, when you're doing the second thing
yes.
for the first one?
But initially we do the back prop, but we fix the descriptor. So those weights are fixed.
Yeah.
Then, now that these two are trained, we can train the detector, which, as you may recall, operates given the other two. And in all of this, it works. So it's comparatively easy to deal with because we have this end-to-end differentiability. And then when the whole thing is trained, you can do fine-tuning and optimize all the weights together if you want. We tried, but it turns out that it doesn't make it improves a little bit, but it's not terribly significant.
It's not clear why you went from top to bottom as opposed to the bottom to top, besides computational reasons.
It's because all of these things are if you think about the descriptor, the orientation was we trained to find the best orientation for the descriptor we want to use.
Yeah. And I can do the same argument given points I'm detecting. I need to compute the right orientation for them. I'm just curious, what was the guiding strategy here?
Well, I assume that the metrics are related to eventually like how many features match at the end, right? So
Yeah.
if you go from the end forward, your train can train the exact same metric on the output.
Yeah. But yeah, I think
we can let's
we can discuss a little
we
bit,
can
yeah.
discuss this afterwards because I'm not. I'm not sure how we would do it.
Yeah. So that's why I'm saying maybe computational reasons, or maybe the fact that if you start from the top, you actually start with what you care about.
Yeah, in some sense, but
If the error percolates down,
Right.
I mean that's at least you're taking care of that.
I think the honest answer is because it seemed natural at the time.
Yeah, I'm thinking about like when people start thinking about SIFT and other feature points, right? Detectors were the first they worked on,
Right.
and then they worked on the orientation and the descriptor. I mean,
Right.
that's how I thought. So,
Right.
The thing is, without the descriptor, you can't do the matching. Without doing the matching, you don't have this loss function. So I think even when people were handcrafting the detectors, they were using their favorite descriptor.
To evaluate it, yeah.
Yeah.
Right.
It's kind of like
Okay, so this is the quadruplet thing is the training. At runtime, it's easier. Is we have essentially these many layers, and what we do is we actually run the detector by itself, so the lower levels of the net on the pyramid, and do non-maximum suppression, because here we don't care about differentiability anymore. We just want interest points. So we do that, and then on these interest points, we run the rest of the network, the one that computes the orientation, and then the descriptor. And that essentially gives us, at the end, a descriptor in the usual sense of the term that we can plug in into your favorite application. So here are a few comparisons. Again, it's the same display, is that when we use our approach, we get far more correct matches than when you use SIFT. And we've actually trained that, of course, on, as usual, on all the usual data sets. Whether we've tested that on all the usual data sets. We here is, so that's Frankfurt, same idea. Yes. And the inevitable bar graphs. So we end up with a not insubstantial jump in performance by essentially optimizing all these elements so that they work together. And there are two versions of our approach. So the one I'm calling Piccadilly, that's depending on which, it's the same pipeline. It just we trained it on one data set or the other. And again, if we had access to, say, what's the Microsoft one? Sorry, I know the.
Daisy.
No, your data set, your the equivalent of Google Earth.
Oh, what is it?
Big map, right? Okay, one of those for the whole world, and the computational power to go along with it. I suspect, it would be worth trying, that these bars would go further up.
How does end-to-end learning would compare with, you had 3 components that you just plug them without doing anything?
It's okay. So I should. It doesn't work as well because it would be. I don't have the exact. But since they are really, I think if you didn't do anything, it would be like all the others. I said the individual components are better, but when you put them together, they haven't learned to speak to each other. So you would be about at the same level as everyone else, I think.
More of a logistic question. So how much RAM do you need? Like, let's say I don't have the GPU anymore and I'm just doing feed forward, right? So, so how much RAM do you need to represent each of the 3, or let's say in total, 3 subnetworks?
I haven't really thought about that. I mean,
Yeah, you know why I'm asking, right? Because
yes, I know what you're asking, but
but
I think that
Feed forward is easy. You don't have to
But
store the intermediate layer. You just have to store the network parameters.
yeah, but the network that's not trivial, right?
right. So I think, I mean, we are going to try to do a project with a small Irish company that has what they have is something that looks like USB key, except it's not memory. It's a processor. Yeah, I'm sure they're not the only one, but they happen to be the ones we know. Well, Movidius, exactly. So I think for them it's no problem.
Yeah.
So if you put that on your drone, it's done.
But then what's the latency? Because now everything has to go through the USB bus, right?
Okay, so these are okay. So I don't know the answers to that, but that's
no. But I'm just saying that will come up, like
right.
You know,
Yeah.
right.
Okay, and something that's okay. So we have 17 years have gone by, and SIFT is still essentially competitive, with VGG being the number 2. Yes.
There are also various works from last year where they use triplets when they train a network for correspondence, like PNN-net from Oxford. And they advertise that if you have one positive and two negative pairs of features, works better than having pairs.
Yeah.
How this compares with Quadruplet?
But it's, I think that's, I'm not completely familiar with this specific paper, but I think that's what we're doing. We have the two positive and the one negative.
Right.
And we need a fourth because there are two kinds of negative. It's in the interest point, it doesn't match, or it's not even an interest point. So it's the same flavor, at least. Okay, so to conclude, we have implemented the whole pipeline end to end. It's a CNN now. We can train it, and we cannot perform the state of the art. Again, the key is that because they are all CNNs, the various components can talk to each other and be optimized to work with each other, and that's, I think, where the power of the approach comes from. And so we are putting all this is on the web. So the detector by itself, the orientation estimator, the descriptors, and this is coming. It'll be there soon. And of course, we hope that you will play with it and tell us what you think about it. And I think that's it. Thank you very much.
We have a few minutes for the questions, so
Sure.
We have actually a lot of time for questions.
so are the descriptors matched using L2 distance, or is this like a custom distance, or?
In this case, it's L2 distance.
Okay.
But it's not, it doesn't have to be.
Okay. Yeah. Well, you can, yeah. That was one question. Second question is, so what is the processing time of the detection? Is it in the article at least?
I think it is.
What's the like? Is it like in seconds or in milliseconds for like a one?
I think, as I said, the numbers I have is about, say, a factor 5 as compared to SIFT.
Okay. Also for detection.
For the whole thing.
Okay.
I mean, because it's all CNN. You replace a standard algorithm by a CNN, and okay, so it computes more.
GPU.
Yeah.
That's on GPU.
On GPU. But soon enough, I suspect our phones will have something that runs CNN. So, which actually is, of course, going to reinforce the dominance of CNN since they start doing hardware, specialized hardware for it anywhere then now.
So I was wondering, there was a work a few years ago from UCLA. So Stefano Suato and I think one of his colleagues. There's this paper, the only thing I remember is the name. It was called DSP SIFT. Do you recall this work? They were basically doing spatial pooling across the whole pyramid. And they, the takeaway from that paper, I remember, was that traditionally SIFT was hand engineered. The detector was hand engineered to find the scale. In the pyramid, you pick a scale and you take a patch from that layer of the pyramid, and then build your descriptor.
Right.
Instead, I think the major modification they were suggesting was take the patches from the whole pyramid, essentially across all scales, and then compute a descriptor. But the descriptor calculation is still a histogram and normalization, let's say. And they also showed like remarkable boost in accuracy just by, I think, doing that. And I was curious because here CNN is still learning to take the patch from a selected scale.
Yeah, it doesn't have this component because at some point deep in the barrels there is a scale prediction similar to the. So yes, it's still original SIFT-like. It doesn't have this component.
But I think the detector somehow, because it's a CNN, I think the advantage of CNNs are that they have these receptive fields which are much larger, right? And so I think in the detector stage, when you get an interest point at a certain location, in your work, the receptive fields are probably pretty large. Right?
We work on I had the dimension somewhere. It was 64. No. Yes. Okay, so here they are. Okay, so the dimensions, the patches we work on are 128, 128. And we built a descriptor for 64. Within that 128 by 128, we look for an optimal 64 by 64. And we built a descriptor for that.
Right, which means that actually pixels in that 128 by 128 patch are influencing
the whole thing,
center of the
Right.
key frame.
So that might help. I mean, in some sense, implicit, then maybe implicitly it's doing something like what you described. Yes.
So there was a paper from Thomas Brock's group where they compared CNNs with SIF. And then this year, I belong to Stefan's Lato group.
Oh, okay.
So we saw, basically we don't touch the orientation module and the descriptor module, we use SIF. And we only change the first part, that is the detector. And by sampling carefully the domain size orbit at the detection part, we saw that we do better than CNNs for Oxford and Fisher datasets, Ecologic. But later we compare for phototourism datasets, and we see that the benefits are not that big. So I think we don't do better than this framework.
Well, the problem is, okay, so Mikolajczyk original dataset was really very specific. It has bias, so you have to be a little bit careful about the...
Fisher dataset from Thomas Brock's group, it's quite bigger with more extreme deformations, for blur, zoom, perspective are fine. So for this dataset we do better, but one reason is also maybe because we train on this dataset. But yeah.
Yeah, there's actually one data set, I don't know, Pascal, if you probably are aware, or you have probably used it. I think it came out last year. It's from Oxford, from Paul Newman's and Ingmar's group, where they have basically taken their autonomous car and driven it around.
Where? Around where? Sorry.
Around
London?
Near London or Oxford, for like the same route. They have done it for like every day of the year for many years. So it's like 100 terabytes.
Right.
So you have like extremely precise point clouds as well as
Sure.
So basically the whole reason is because they wanted like this test can our algorithms do invariance.
Okay, so maybe that sounds interesting.
Yeah. But it's a huge data set, so
right.
Again, computational challenges, right? Like how many GPUs have you got, right? That kind of issue comes up.
Right.
So thinking about end-to-end learning, so how would we take something like that and move to image level? So instead of patches, like I say, all right, I know there exists X, right? And then, so the holy grail.
Yeah, well, you want me to solve the whole vision problem?
I mean, I wish. But your thoughts on like how, architectures like these, right? Is there a possibility of pushing in those levels, or?
I hope not. That's the only reason. The only thing I can say, I don't know, because that would put us out of a job. I still hope there is some room for actually thinking about how to organize the problem to get the results we want. But
in fact, like in this book as well, it looks like you had to do a lot of legwork trying to understand each of the components, right? And then infuse that knowledge into the thing, right?
I think it's implicitly there. So when you asked, why did you do it this way? I didn't give you a very good answer, but I think it's also because we are used to, we kind of know, having played with this for 15 years, that that's probably the right way to do it. But
You tried using color?
we use color. The Oxford dataset has color in it, which actually is one of the reasons that I think the one we train on Oxford is better than the one we train on the Roman forum, because it's more colorful. But we are not using it in a smart way. So my colleague Sabine Sustrug would probably.
This bit quite elegantly answer the question, is color useful?
Yes, it is.
Okay.
Great.
That's great.